Hello, everybody, and welcome to the Europlanet Science Congress 2024 at the Freie Universität in Berlin. We're very, very glad to have you here today. We have two back-to-back press briefings, one about ESA's Hera mission, which will launch in about a month, and then that will be followed by updates on the BepiColombo mission, which did a flyby of Mercury, the closest flyby ever of a planet, last week. We are just waiting for some of our speakers to arrive. It's a very, very packed day here at EPSC. So there are sessions going on at the moment, and they are moderating and coming along as soon as they can. So just in the meantime, I'm going to say a little bit about EPSC. So we started here in Berlin back in 2006. The first Europlanet Science Congress was held here at the Estrel Center. That was for about 500 people, and that was really the first big meeting that we had in Europe for planetary science. We've held that meeting annually ever since, sometimes in collaboration with our colleagues from the American Astronomical Society's Division of Planetary Sciences. And this is the third time that we visited Berlin, and we have our speakers, so this is great. So if you want to sit here and here. Here and here. Yes, thank you. In fact, actually, yeah, there we go. Great. Okay. Yes, so we're in Berlin for the third time. We have 1,200 people this time registered for the meeting. We've covered the spectrum of planetary science this week. So because we are quite short of time, we are going to crack on. I think our first two speakers with who will be talking about the Hera mission are Patrick. Michelle, you're going first, yes? Yeah. Yes, followed by Dr. Michael Küppers, who's the ESA Hera project scientist. So, Patrick, you can switch your slides by yes, and if I give the mouse to Michael, then you will be able to switch through as well.
So, you mean I use...
There we go.
Okay, so I hope you hear me. Okay, so thank you, and sorry we're a little late, but so this is just an update on the Hera mission about a month or 3 weeks before launch. We did just prepare a few slides just to give an overview. So basically, as you know, Hera takes place in the framework of the IDA collaboration. So IDA stands for Asteroid Impact and Deflection Assessment. It's international collaboration that supports DART and Hera. So you know that DART made successfully an impact on September 2022, September 26, on the small moon called Dimorphos of the asteroid Didymos to deflect its trajectory around its main body and reduce the orbital period, which was originally 11 hours and 55 minutes by 33 minutes. So it's a very successful first deflection test. There were a lot of results extracted from the DART images and also the small Italian CubeSat Alicia cube. But there are many unknown that I would just speak about to be clarified in 2027. And in particular, these are the images that we have of Didymos and Dimorphos. On the bottom left, you have Dimorphos before impact. And the very interesting thing is that although we go to see the same body, we already know it won't look like it looks like on this image, because of course there was an impact and therefore something happened, and we actually have we are very excited to go back and see what it looks like, because from the DART and Alicia cube data, there are different ways to interpret them and different solutions for what is now Dimorphos. And in particular, the best solution is maybe that it was totally reshaped. So there was a global reshaping, like if the crater was bigger than the asteroid itself. So the shape has changed. Or if this is wrong, there may be a crater, and we want to know also the size and the depth. So for the moment, we believe it's reshaped, but we have to see. And this is why we need to do Hera. The other thing that we want to understand is all the properties of the asteroids, in particular the internal ones. This will be the first time that we do internal probing of an asteroid using a low-frequency radar on a CubeSat. And this is important because from these images, it looks like Dimorphos is what we call a rubble pile, which is an agglomerate of boulders held together by gravity. Maybe the side distribution of boulders that you see on the image are the same inside, or it may be also a solid core surrounded by gravel and pebbles. And this, of course, has different implications on how we interpret the response of the asteroid to the impact and for the modeling of the impact itself, which needs to start with the correct structure. So in other words, what I'm not sure what I have afterwards. Yes. In other words, what ERA wants to provide is a full documentation of this first deflection experiment so that modeling tools can be validated at asteroid scale, and validated meaning able to reproduce the final state of Dimorphos that Hera will provide, but also using as few free parameters as possible, because being a modeler myself, I can provide any answer you want by using free parameters, which may be unrealistic. In that case, my simulations are wrong. So what we want is to make sure that these models are correct by reducing the number of free parameters so that they can be extrapolated to other scenarios, other cases, etc. So this is what ERA will do. We are very excited, and also a lot of science, because this is a binary system and we have binary formation models that also want to be checked and that depend on the results of Hera. So there are a lot of great implications. The science team is wonderful and works actively towards being prepared to the data analysis and interpretation. With this, I think I leave the stage to Michael, who's going to tell you about the mission scenario.
Yes, as you probably know, Hera will be launched in October this year, with the launch window opening on the 7th of October. We will get the first images actually a couple of days after of the Earth and the Moon. And then in March next year, during cruise, we will fly by Mars. I will talk a little bit more about this later. Then arrival at the asteroid is it's in late 2026, so there are around 2 years of cruise phase. And actually, the navigation strategy then at the asteroid is derived from Rosetta. So we have first an early characterization from some distance to be confident that we know the system very well. Then the 2 CubeSats that are traveling there with Hera are released and will perform their independent investigation of the system, including a radar investigation of the asteroids. That's the first time that the interior of asteroids is investigated with them. And so we will have a phase of 6 weeks or so of detailed characterization of the asteroids from a distance of maybe 10 kilometers with the CubeSats and Hera together. And then all the spacecraft will essentially get closer and closer with a form of fast flybys down at the end to a distance of less than 1 kilometer from Dimorphos, from the Moon. And the end of mission is for Juventus, for one of the CubeSats, definitively to land on Dimorphos. Milani is most likely also to land, with the details still under discussion. And for Hera, we are also still discussing the end of mission scenario, possibly a landing on Didymos, on the first one. Going now again to the near future. So the Hera and its CubeSats are now at Kennedy Space Center. They arrived there a week ago on the 3rd of September. Some last tests are now performed there, also to check that nothing went wrong with the transport. And so launch will be in for about 4 weeks from now, with the window opening 7th of October. And then the cruise phase after some Earth-Moon commissioning, the highlight of the cruise will be the Mars flyby. Here is a little bit a demonstration of the geometry. And the flyby will be, the Mars swingby will be tuned that we get a close approach of Dimorphos, of the outer moon of Mars. And So we will see the site pointing away from Mars at high resolution, and because most famous observations so far from Mars orbiting spacecraft that orbit inside, this is a relatively little explored part of the moon. There are data from the Emirates Mars mission that can be seen there on the left-hand side, which has a very eccentric orbit, but we will complement this also with data taken at a different wavelengths. And then, okay, we have another 1.5 years of cruise, and Hera will arrive at its target asteroid. I believe we thank for your attention, and this is now open for questions.
Just adding one thing, which I think is really exciting, that this is the first time we will land on such a small object, like 150 meters with a CubeSat. And this is the first mission that use a mother spacecraft and 2 CubeSats for a deep space exploration. So that's also, I think, very exciting.
Thank you very much, Patrick and Michael. I'm just going to briefly hand over to my colleague Callum, who will just tell you about housekeeping and asking questions for the virtual participants.
Okay, so for those of us joining online, please post your questions in the Q&A tab on Zoom. For those of us in the room, it seems we've already sussed this with microphones already, but the camera will follow whichever microphone is active. There can only be one microphone active at any one time. So when you wish to speak, turn your microphone on, the camera will rotate to you as it has here to me. If you try to turn on your microphone while somebody else is still speaking, it will turn theirs off and turn to you. So one speaker at a time, please. Yes, for those online, please post your questions in the Q&A and we will start to take them.
Thank you. Thank you. Does anybody have any questions here? Got journalists in the room here. So, Patrick, what are you most excited about?
Well, I'm most excited about the launch for now, because this is only in a few weeks, and it was in Europe 20 years of effort to get there. From the very start of the story. And so it's like giving birth to a baby that waited 20 years in your stomach. So I don't know how it feels already for 9 months, so 20 years. So yes, that's the first excitement. And then for the mission itself is really to see now Dimorphos. I mean, we have these spectacular images before impact by DART. We have simulation, but we want to know what's about Dimorphos now. So I think that's what excites me the most. Yeah.
Thank you. And how about you?
Yeah, for me on such a mission, the most exciting part is maybe actually the approach to the target when you get more and more detail. And okay, in this case, we have some prior information from that, but we want to see what has changed. And when you get closer and get more and more information, this is really the most exciting. In a sense, it's a very dynamic part of the mission.
I will add that this is exactly correct. I mean, the two of us have already experiencing first images of a new world, with Rosetta and even the flybys of Stein, Lutetia. And I was involved in OSIRIS-REx, Hayabusa 2, etc. So, and each time, you have your assumptions, and then when you have the first images of the new worlds, it's absolutely crazy. It's a feeling that I think cannot be described with words, and we'll have the same with Dimorphos. So you mean what kind of size we are able to deflect, I suppose? Yeah. Depend on the technique. So with a kinetic impactor technique, like DART, we can target asteroids of 100 or a few hundred meter size at most. It also depends how long you can do it in advance. With the efficiency of DART, if we transpose to a trajectory around the Earth, around the Sun, assuming the efficiency of DART, then we need still decades to do it decades in advance so that it misses the Earth. So these are techniques that are still, not super strong, I would say. And therefore, we need to do it in advance if we are targeting an object of a few hundred meters in size. Of course, the smaller the object, the sooner you can do it when it comes to the Earth. But I would say this technique is more for objects from 100 to a few hundred of meters at most. For smaller objects, you could also use a gravity tractor, which is a spacecraft that you put at proximity of an asteroid. You don't touch it, and you just use a gravitational force to attract the asteroid toward the spacecraft, and therefore you can deflect it, and that can maybe work for objects of a few tens of meters to 100 of meters. Bigger objects, we need maybe other techniques, but we don't know any threatening object of larger size, and we know most of the objects larger than 1 kilometer. We have no reason to be worried for our lifetime, and even longer, because the impact frequency is every 500,000 years.
Yeah, just to end, as Patrick said, it depends a lot when those objects are detected. If we have ever something bigger than that, for small asteroid, maybe 10 years warning time would be okay. It's indeed it's a key point as also detection programs. The asteroid has to be detected, and also the orbit to be determined to that accuracy that we know that the impact will happen if we don't do anything. And if in the worst case, a nuclear standoff explosion could be more efficient for a somewhat bigger object, and also this would not mean that the asteroid is blasted in pieces with a nuclear bomb. It would be a standoff explosion at some distance to push it away. This would be somewhat more efficient than a kinetic impact, but of course, generally the nuclear option would anyway be tried to be avoided.
And if I can add, the key is therefore the anticipation. And the good news, and this is the advantage of this risk, is that we have means to do something about it with things which are feasible. And for the anticipation, the NASA should launch the NEO Surveyor mission in 2028, maybe 2029, 2028, 2029. And this is a mission that is planned to make the inventory of 2/3 of all threatening objects larger than 140 meters in 5 years, and more than 90% of them in 10 years, including orbit determination and size, because it has an infrared band. And therefore, I would say by 2040, to be flexible, we should have a great knowledge of the threat at short term, probably zero, but also a great asset, which is the possibility to anticipate, because we'll know all these objects, we'll know their orbits, we can follow them up. And this is a key. And this is why it's also important to prepare for deflection techniques to be ready, because once we are able to anticipate, then we know if something comes to us, and if it comes to us and we can do nothing, then it's too bad. So that's why we also in parallel have to do this kind of deflection test and characterization, because what we learn from that, and Hera will confirm, is that it's highly important to determine the properties of the object, because the impact response or deflection response, I would say, highly depend on them. So having a possibility to keep characterizing those objects, to keep learning how they respond to an external force, which is sometimes very counterintuitive, as we have seen in the past, is very important. And this is why also ESA is preparing another mission called Ramses to visit Apophis in 2029, which is another, hopefully, for sure, will not impact the Earth at that time, but it's in this population of near-Earth objects, and we need to better understand them. So characterization and deflection tests are part of this planetary defense objectives with orbit determination discovery.
I think we've got another question online, but are there any questions in the room first? No, in that case, Callum.
Okay, we have several questions online. Ludwig asks, do we know what Dimorphos is made of, iron or carbon?
So Dimorphos, based on spectra, is essentially made of silicates. So olivine, pyroxene, it's part of, so you have two main classes of asteroids, S and C types. S class are silicate types, stony asteroids made of, stony minerals. And then C type, which is made of carbon, even phyllosilicates, so hydrated minerals, etc. So Dimorphos is in this S class, which is made of olivine, pyroxene, some iron, but it's not the it's not the essential part of the asteroid. And sorry, just to finish on that, for this type of asteroids, we already know which kind of meteorite they are their analog, because another asteroid of this class called Itokawa had the samples returned by the Hayabusa Japanese mission. And by analyzing the sample, there was a perfect match with what we call LL ordinary chondrites, which are low iron ordinary chondrites. So we also know the properties in details because we have samples in the lab for the same class.
And maybe one more point to add, we have instruments on board in the visible and near infrared that will measure the spectra throughout the asteroids and will find out if there's any mixture from other types of asteroids which could happen through impacts, for example.
Okay, thank you, James. Sophie asks, please tell us more about the instruments on board and what exactly they will do.
Okay, so we have 3 spacecraft. So I start with the main Hera spacecraft. We have 2 cameras on board who have the dual purpose of navigation in the asteroid system and as scientific imagers, so to look essentially how the asteroids look like in detail. And in the very late phase for the moon, we will go down to centimeter resolution. We have a visible near-infrared spectrometer on board to look at the composition of the asteroid. We have a thermal imager to measure the temperature of the asteroids in the further infrared, which also allows us to determine the physical properties of the surface area. Then we have a laser that measures the distance and supports the determination of the detailed shape, and which allows us again to understand better the processes on the asteroid surface. And a radio science instrument that essentially gets information about the gravity field from the deflection of the spacecraft motion by the presence of the asteroids, and also from the inter-satellite link that communicates between the main spacecraft and the 2 CubeSats. Then the first CubeSat, Juventus, carries a radar that essentially looks below the surface of the asteroids down to the depth of several tens of meters. So this is the first time that we really investigate the interior of an asteroid. And it also carries a gravimeter that will essentially measure the gravity when the CubeSat lands, and potentially bounces also the gravity at various positions on Dimorphos. The second CubeSat, Milani, has a visible infrared spectrometer, again to measure compositions with a somewhat wider wavelength range, and a dust detector that will detect the amount of any fine dust that may be in the system, and also try to get some measure of its composition. Have I forgotten something?
It's not a science instrument, but the accelerometers on board the CubeSat, which can allow us to get a sort of measurement of the bouncing properties, like how much is absorbed by the low velocity impact of the CubeSat, which is important because, as I said, each time we interacted so far with an asteroid, whether it is to take a sample or make an impact, we had a sort of a counterintuitive behavior. So images do not tell us all. We need to touch in some way, and we'll have this possibility with the landing of the CubeSat and the accelerometer that can give us some information on how it bounced.
Callum, we've got more questions online.
We do. Daniel asks, there was a fascinatingly shaped and long-lived dust structure left around the system after the impact. Do we know whether any of that dust is still lingering there and may either be studied by Hera or pose a danger to the spacecraft?
So Michael contributed to a study showing that some of the dust may produce meteors, but very small, so on Earth and Mars. In the system, so all the small dust, like centimeter size, is ejected by solar radiation pressure from the system very efficiently, and we have actually a very long tail that was observed by the Hubble Space Telescope, more than 10,000 kilometers. Now, in terms of macroscopic borders like meter size, etc., we cannot rule out that some of them are trapped in the system on some of sort of stable orbits. We have some studies showing that it may happen, but they don't pose too much risk because they are not going at very high speed. And ESA knows how to do that. They explored an active comet with Rosetta, so that shouldn't pose any danger.
Okay, we've got a question from Torsten in the room.
Yeah, Torsten Krenning, Spacewatch Global. Listening to your excitement about the mission is great, but how do you transport it to the general public, to the politicians? So what is planned on the outreach side for the launch and for the entire mission to really engage with those people that finance it at the end of the day? Because we're talking about shrinking space budgets and so on and so forth. So how do you keep this momentum transported to the general public and the politicians?
Okay, I can provide my experience, but ESA is going to communicate a lot around the launch. There will be a launch kit, etc. We'll do a lot of things, and we already do a lot. We have a documentary also that will come out on France 5 in October around the launch, explaining about that and Hera. So to answer your question is not easy because we already have the media and public excitement for this topic. You know, asteroids, planetary defense is clear. And yet, politicians are not necessarily super sensitive to that. So if you have a solution for that, we are taking it because we do all the efforts for the public. For sure, we do conferences. ESA is doing a marvelous work in terms of education. We also do cartoons in different languages for the children. When we talk about this mission, we have a lot of people coming to the talks. The journals keep talking about it everywhere. So there is a mismatch between the media and the public attention and the politicians. Although, you know, in the US, it's not the case because planetary defense is considered a very important topic, and even at White House level, the reports come out from the White House. And to just give you an anecdote to show the mismatch, so I'm personally in some of these international group working with the UN, etc. on the field. When I go to the US, I see the US representative at White House level, and he says, "Oh, Dr. Michel, thanks to you, it's great that France is taking care of it." No, that's just me. I'm not France. Actually, I don't know even if France does know that the topic exists. So effectively, I don't have a good answer to that. But what I can say for ESA, at least, and every one of us, scientists, etc., we do the job for the public because we know they love it, and we know it's a great way to inspire the young generation with great challenges, give them the test of knowledge, etc., which we need for them to solve the issue they will have to solve on Earth. And this topic serves well the purpose, but now I don't know how to tell that to the politicians.
I think we're going to do just one more question now for Hera, and then we're going to move to the BepiColombo briefing. But if there are more questions for Hera, Patrick and Michel will be around, and we can follow up later. So one more column.
Thank you. So Shamila asks, would the Hera mission be able to confirm whether DART's impact indeed caused Dimorphos to wobble, as some observations suggest? If so, would you be able to share what the process of observing Dimorphos to measure the wobble would look like?
So the answer is yes. Any wobble motion or any irregular motion of Dimorphos will be found. And actually, because we don't really know what specific to expect, there is no specific procedure. It will just happen through the regular imaging that will already be done for other purposes.
And I will add at this point that, you know, for the scientist, the most crazy solution is the most exciting, right? But for the engineer that do the operations, it's not cool. And in fact, I just really want to acknowledge the amazing work that the project team of Hera did to implement a mission so quickly, because from 4 years, from basically from the approval to 5 years to the launch, it's very short in the space business. And the operation people are really working actively with us to be prepared with something that, as I said, we don't know what will be, and effectively we may have some tumbling motion and things that are beyond what we expect because we may have surprises, and so they have to get prepared.
Thank you very much. So I'd like to thank Michael and Patrick for the moment. And I'd like to invite the BepiColombo team to come up here.
Thank you.
And please stay around if there are more questions, and hopefully we'll get to them later. So I'd like now to invite Johannes Benkhoff to introduce the BepiColombo team. Johannes is the project scientist from ESA. So Johannes, over to you.
Yeah, thank you, Anita. Thank you for giving us the opportunity that today we can talk about our last swing by and show you some first results. Yeah, I brought here a big team of representatives from different area and experts. To the left, I have Ignacio Clerigo, sorry, he is the ESA BepiColombo spacecraft operation managers. Then next to him, we have Yasumasa Kasaba-san. He is from the Planetary Plasma and Atmospheric Research Center from the Tohoku University in Japan. He is part of the MEO spacecraft PIs. He is a PI of the PWI instrument, Plasma Wave Investigations. Then we have Helle Wilhelmsen. She's from the Swedish Institute of Space Physics and co-I on the Serena instrument. Then we have here to the right, Jack Wright. He's a research fellow with ESA. And to the far right, it's Isabella Krull, a young year scientist working at the Technical University in Dortmund and also together with the University of Bremen. And then next to me, I have Garen Jones. At the moment, we have 2 project scientists at ESA for BepiColombo because we are in a transition phase. Although I think such a complex and big mission like BepiColombo would deserve 2 project scientists. And together with Garen, I will now guide you through what we had planned for you this morning. But before we start, I will do a brief summarize of what BepiColombo is about for those who are maybe not 100% familiar. BepiColombo is a joint mission between the European Space Agency, ESA, and the Japanese exploration agency, JAXA. And the goal is to do a very comprehensive mission to explore Mercury. And to do so, we will send 2 spacecraft to Mercury, 1 spacecraft provided by the Japanese Space Agency called MEO. And on MEO, we have 5 instruments, and you will hear more about MEO from Kasaba-san and the first results. Then we have the MPO, which is a Mercury planetary orbiter. It's an ESA-provided spacecraft with 11 instruments on board. And all in all, these instruments have these scientific objectives, which are listed here, to look at Mercury and planet formation processes, to describe the internal structure, physical characterization. We look at the surface composition, interaction with the environment, magnetosphere, exosphere, and we can even do some science beyond Mercury, like studying general relativity. We launched, as I said, in October 2018. The mission is at the moment in cruise phase. That means that the 2 spacecraft are stuck together on top of a transfer module, which brings our 2 spacecraft to Mercury. And then in late 26, we will be separated from the transfer module and then going into orbit. next milestone will be another flyby in December, but before we go there, I would like now to ask Ignacio to give you a little bit updates on the spacecraft status and from the last flyby.
So thank you very much, Johannes. So I will present the Mercury Swingby 4 from the perspective of the spacecraft operations. But I would like to start saying that flying and operating that complex machine is really a true team effort. And I would really like to give credit to the flight control team and especially to the flight dynamics team that do this, for me, still marvelous thing of targeting a planet from millions of kilometers away and safely fly at only 165 kilometers from the surface. It's really an engineering achievement. So why we need flyby? So we have an electric propulsion subsystem. Is with the amount of fuel we have on board, it can provide a significant amount of change of velocity, 5.5 kilometers per second. But this is not enough. So to reach Mercury, we need much more. And what we do is we use what we call planetary swingbys, where we actively use the gravity of the planet to change our velocity with respect to the sun. So I will not go, of course, into the equations. At the end, the velocity is the same, but we just change the direction with respect to the sun. So we need to do that 9 times in the mission. So far, we have fly by the Earth, Venus 2 times, and Mercury now 4 times. And today we'll talk about the latest flyby, the 4th Mercury flyby on the 4th of September. So you have first, of course, there will be nicer pictures later, but you have one picture that makes us very proud, where you can see Mercury on this latest flyby on the 4th of September. We were about 165 kilometers from the surface of the planet. Our flight dynamics teams prefer to talk about distance, perihelm distance from the center of the planet, because it's always tricky to define what do you take as the reference. And this flyby, the main goal of this flyby was to reduce the heliocentric velocity. So after this flyby, we are now in a one-to-one resonance with Mercury. So we are at the same sun distance as Mercury, so between 0.3 and 0.46 astronomical units, which now is a major step to get closer to Mercury and to enter the orbit in 2026. And this is just something by chance. We didn't know about it until last week, when talking about how low the altitude of the flyby. We went through the different sources and different authorities on the topic, and we have found out that this was the closest a spacecraft has ever fly by a planet, including the Earth. So, of course, there's other moon or other bodies, comets, etc. But a planet, no one has done a flyby at such low altitude. So, I mean, it was unintended, but of course, it's always a nice aspect to highlight. So it's not only about the trajectory, but also about where, for the science, where we are looking, what is the attitude of the spacecraft at the time of the flyby. And this is what you can see in these images, what was the orientation of the spacecraft as seen from the sun and as seen from the Mercury North Pole. So we went through the terminator side and from the North Pole to the South Pole. And during this time, the time of the close approach, we were mainly pointing the spacecraft and the MEO part, the MEO spacecraft that is on the top, it was the one that was pointing towards Mercury at the time of the close approach. Of course, it's covered by the sun shield, so it's not that it has perfect visibility, but it managed to get very useful data if it's pointing towards Mercury. And then once after the moment of closest approach, Mercury was in the -X side of the spacecraft, where we have Serena and MGNS that are also 2 of the instruments that are providing very interesting data from the flybys. So we operated MEO and most of the instruments on the MEO side. This is done by our Japanese colleagues. They will briefly talk about it later. And on the MPO side, on the ESA spacecraft, we operated all the instruments that were not covered by the Mercury transfer module. So unfortunately, the main cameras, the scientific cameras, are covered. Also, the altimeter, but and Mercury is the infrared camera, but the rest of the instruments were operated. And as you have already seen, we also have these cameras made for outreach purposes, and we started taking images immediately after close approach, not before, because we're approaching from the dark side, so there's not much to see. But then after that, we have 120 images, and they will be available in the ESA Planetary Science Archive, I think, starting from today. So what is after, you may ask? So we have a very intense year ahead. So we have another flyby in December, 1st of December, Mercury swing by 6, and another flyby in January, 8th of January, 2025. So that's like 3 flybys in less than 4 months. We have never had such intense phase of planetary flybys. And after that, the original plan was to arrive to Mercury in December 2025. For that, we have a period, almost 1 year, of continuous use of the electric propulsion subsystem. What you may have heard is that we have a major anomaly in April this year, and because of that, we cannot extract all the power we need from the solar rays to operate the electric propulsion at the full thrust, so we have to reduce slightly the thrust level. And the problem is that because this phase was very dense in terms of thrusting, we are not able to do to implement the original trajectory as foreseen. So, but okay, it's upsetting, but we have a simple solution that we will just apply this lower thrust level, and we just have added 4 revolutions more around the sun. So this is about 1 Mercury year more. And with that, we can just distribute the amount of thrust we need to do in more time, and it will reach Mercury in November 26. So we are still working on the consolidating the trajectory. Dates are preliminary, but we are expecting to separate the propulsion module in September, October timeframe. 21st of November 26 will be the day of the Mercury orbit insertion, so where we will start, we will be bounded to the planet and start orbiting the planet. 9th of December will be the day we will say bye to our Japanese colleagues and we'll separate the MEO spacecraft. Then we will separate the sun shield. And then, okay, we still need to do a few more maneuvers to reach the science orbit of the MPO. And beginning of March, we will start the commissioning. And hopefully by the end of March, beginning of April, we should be on the science phase. So that's the dates. I mean, that's the plan. It's still a bit of, we need to fine tune the precise dates, but this is where we are going. And I think that's all of my side. So that's the work.
Great, thanks very much, Nacho. So yeah, we'll now have a brief overview of some of the observations made during the flyby of the planets last week. So like the Earth, Mercury has its own magnetic field. So if you stood on the surface holding a compass, it would point towards the magnetic North Pole. And this magnetic field carves out a bubble in space where the solar wind from the sun usually can't reach the surface of the planet. And during this flyby, several of the instruments that were able to operate were able to measure the environment around the planet. So first I'll hand over to Kasaba-san to summarize the observations made by the instruments on the Japanese MEO spacecraft.
Yeah, nice to meet you. I'm Yasamasa Kasaba from Tokyo University. I'm the PI, primary investigator for the plasma wave investigation. It means that electromagnetic waves measurement. However, today, I'm also here as an delegate of JAXA. Practically speaking, I was a payload manager, a payload deputy manager for the starting phase of this mission in MEO side when I was in JAXA before 2010, so that I can have some explanation directly. So here, it is an overview of the MEO status. As I say here, that it is behind the sun shield. It means that just the lower right figure shows that in the cruise configuration, we are sitting in the sun shield, so that our main instrument just looking the side of the spacecraft so that we can only see the just between our side panel and the sun shield. So that here we have a lot of instruments in the mainly the particles, ions, electrons, and low energy, hot and high energy. And also I already mentioned that the plasma instrument and also the magnetic field members and also camera and the dust monitor. But these white instrument can have it is not so much full field of view, but very narrow field of view, but full functional. But including my instrument is a plasma wave instrument, and it has a 50-meter very long wire antenna, but it cannot be deployed without spinning. It means that after the ejection of the spacecraft from the MPO, we can do the full performance, but at the moment, not yet. But unfortunately, we have a messenger spacecraft in 10 years ago, and it also had several good observation. However, the BP also have a more wider capability of measurement, and MEO also has such kind of this. It means that low and medium energy particle measurement, and also the very high sensitivity electromagnetic wave measurement. It can provide the structure of the magnetic field and also magnetosphere with a Mercury. It is very fundamental, but at the moment we don't have a direct knowledge. So that here, next page is the news from the last week, MS Mars Swingby 4. The Mars Swingby, we already have 1 and 2 and 3. And those were executed like dawn to dusk to dawn geometry. It means that an equatorial orbit, so that we knew the very brief view of the local time changes. But this orbit is very fast time measurement from the north to south, very close to the surface. And this orbit, messenger did like a polar orbit. However, the messenger has an upper periapsis just very close to the northern pole, so that it is very fast time to see the southern hemisphere's magnetosphere. And you can see here is that CA means the closest approach. It is very close position to the Mercury. And the usual cases, the left side, it is assigned with the emission result, and it is very usual magnetosphere we expected. It means that it will like comet. So the magnetic field is just a north to south dipole-like, and the blowing from the sun to the tailward, it is a solar wind. It can make a comet-like the magnetic field. In this case, we expected that a very symmetric shape of the magnetosphere. However, you can see that before the close approach, it is almost nothing. And after the close approach, it is a jump of the very drastic change of the hot electron appearing and also ions. It suddenly appears. At the moment, I got this data yesterday, so that I do not have a very clear explanation. I did some discussion with our colleagues by email yesterday. But it may be the time difference, but it may be the structure. Such kind of the separation of the time variability and also the spatial variability, it is not easy to be done only by the one spacecraft. But BepiColombo, after the separation, we have 2 spacecraft. So the collaboration with MPO and the MEO, we will provide the more very good vision for the this very strange Mercury magnetosphere in future. At the moment, I can only say that, it is very strange, but no explanation. For example, the next page shows that previous flybys about it is MSV3, I think. You can see that it is also the equatorial to orbit. It was an exterior orbit, and you can see that upper side shows that particle measurement, and the upper side is hotter one, and the lower side is colder one. And very close to the Mercury, the very hot plasma is just on inside of the completely confined in the magnetosphere. And you can also see the bottom side, it will show the plasma waves. It is measured by my instrument. And you can see that it is very clear and the common boundary between the particle and waves. And I didn't show in the last pages, but I looked in my data yesterday. But my instrument, plasma wave, did not have such a clear boundary, so that it is also the I feel very strange point is that why the north to south structure is very different compared to the east and the south and east and the west structure. Anyway, the next page. It is a messenger result, and the messenger also show in the right side showing that X-ray illumination of the surface, and also the bottom side shows that very rapid changes with the magnetic field measurement, main field. And it is not so easy to be explained, but this result shows that in the equatorial plane, in the statistical point of view, dawn side is more active than dusk side. And it is also another asymmetric feature of the Mercury's magnetosphere, which we need to consider and we need to solve in future. And it is a summary of our Bepi-MEO status. At the moment, we only have a very limited performance of the per measurement, only limited particle measurement. Also, the my PW instrument only measures the magnetic field turbulence, but we cannot measure electric field. So that such a restricted status, but very fragile, small size Mercury magnetosphere. We are now looking at a very brief site, and we don't know it is stable feature or not. But those flybys already show very new issues, and we are waiting the separation of the MEO from the MPO. It becomes 2 years later. And at the moment, my students have a lot of work. It because that they waited the data in next year. But we still need to wait 1 year with some exciting. Thank you very much.
Great, thanks very much, Kasaba-san. We'll pass over immediately to Hayley Williamson to summarize some of the observations made by the SERENA instrument on the MPO spacecraft.
Yes, thanks. As Jean said, I am Hayley Williamson. I'm a senior scientist at the Swedish Institute of Space Physics, and I'm here today representing the entire SERENA package, which is a particle instrument suite on MPO. So SERENA has 4 sensors. We have Elena and Strophio, which are neutral sensors and are currently not capable of taking measurements because of the crew's stack configuration. But then we also have 2 ion instruments, PCAM, the planetary ion camera, and MEPA, the miniature ion precipitation analyzer, which is the instrument that I am actually a part of, that are on the side of MPO. So we have been able to take measurements during all 4 flybys with an unobstructed field of view. So it's very exciting, and I'm very excited to show you the results from both MEPA and PCAM. So starting with the MEPA observations, here again is this diagram of the flyby with respect to the Mercury magnetosphere. And then on the left, we have the MEPA data. So the y-axis here is energy. So stuff towards the top of the plot is higher energy, and the brighter the color is, the more particles we were seeing. And as with the MEO data, actually, we don't really see anything before closest approach. So in sort of this northern hemisphere where we might have expected to see a little bit. And then after closest approach, we see some high energy ions that are gradually decreasing in energy. And then a little bit after closest approach, we see a change in the particles, basically, where they decrease a little bit in counts and they sort of split into 2 separate energy populations. This is very exciting. It's really different from the previous flybys, which I will actually show you in a minute. And then we think maybe this point where the data ends is maybe the magnetopause, which is where Mercury's magnetic field essentially stops blocking the solar wind. Also around this magnetopause, we see some very high energy ions all the way at the top of our energy range. So it'll be very interesting to see what those are. Also, something exciting and different about this flyby for us is we think that we really, for the first time, see planetary ions. MEPA is really designed to measure solar wind ions that are precipitating into Mercury's magnetosphere. So we think that because this flyby did end up being so close to the planet, we did actually see heavier planetary ions. So that's going to be a topic of ongoing analysis. The planetary ion camera, PCAM, is quite similar, has a quite similar field of view to MEPA, but we have slightly different energy ranges. and PChem is specifically designed to measure planetary ions instead of the solar wind like MEPA. And on the bottom here, you can see their data from close to the planet. And it looks fairly similar to the MEPA data, which is good. We usually want to see them looking pretty similar. They also saw some signatures of planetary ions, which again, also good that we saw similar things. PChem also was on and observing the solar wind both before and after closest approach, which is what's on the top here. And they saw some really interesting events. So the day before closest approach, they saw what's called a SEP, or a solar energetic particle event, which is essentially when really high energy particles leave the sun and hit the spacecraft. And this makes a really distinct signature that's essentially noise from the radiation in the instrument. And then a little bit later, they saw a coronal mass ejection, or CME, they think. So this is going to be something that they will study some more to confirm that this is a CME. Which is also exciting too, because that a CME will have really dramatic effects on the magnetosphere of Mercury. So that might explain some of the maybe unexpected features of the data that we see, like that the boundary positions are maybe not so much where we would expect them to be. They also saw what they think maybe is a second SEP event after the flyby as well, which is on the top right here. So there's a lot here for future analysis. So with the previous 3 flybys on the MEPA team, we like to say that even though all the trajectories were quite similar for the first 3, we had 3 flybys but 3 basically different magnetospheres. And now with this 4th flyby looking even more different, we can say we have 4 flybys and 4 magnetospheres. So this is basically in order from 1, 2, 3, and 4. So for the first 3, the closest approach is essentially lined up sort of just to the right of the center. Then with the various magnetopause and bow-shot crossings marked. And yeah, they all look quite different. And it really shows just how dynamic Mercury's space environment is because it is so small and it is so affected by the solar wind. So that even when we pass through the same regions, we see different particle populations. And now when we've passed through completely different regions through this terminator pole region, this is stuff that we have not been able to see at all in the previous flybys. So this is essentially just in cylindrical coordinates, a diagram of the trajectories and where we saw the boundary crossings in MEPA data compared to what Messenger saw for the magnetopause in orange and the bow-shock in blue. And so this the 3 that are sort of on the left are the previous 3 swing-bys with closest approach with the stars close to the planet. And then in black is this one that happened last week. And you can see just how different it is, how the closest approach is really in a completely different part of the planet. And then you can also see I don't know if you can see this cross, that's what we think is the magnetopause crossing, and it's in a very different place from the previous magnetopause crossing. So this is all incredibly interesting. It's not necessarily what we might have expected. And we on the Serena team are very excited to further analyze our data.
Great, thanks very much, Hayley. So one, well, there are actually more than one instruments of this type on BepiColombo. Magnetometer. So magnetometer measures the strength and the direction of the magnetic field, and the magnetometer on MPO measured the strength of the magnetic field during this flyby. So instead of just showing a plot, this has been turned into sound. Obviously, it's not real sound. It's just a way of presenting the data. So the strength of the sounds you'll hear in a moment, covering about a minute, represents the strength of the magnetic field. And then the sounds you hear are a conversion of the fluctuations in the magnetic field during the flyby. It sounds a bit weird, but let's play it and listen to last week's flyby of Mercury. Yes. Yeah, so I'll speak of the last bit in the interest of time. So some of those fluctuations aren't fully understood yet. Some may still be some spacecraft effects, but yeah, the magnetometer team working with the data from the members of the other in situ instrument teams will have a busy few months ahead studying the data from this flyby and interpreting what on earth was going on in the environment immediately surrounding Mercury. So we'll hand back now to Johannes.
Yeah, thanks, Geraint. Now it would be the time to show you us wonderful images from our stereo or high resolution camera on board. But unfortunately, this camera is blocked to the stock configuration and looks directly at the transfer module. But fortunately, we also have some monitoring cameras on board, which were very late introduced to BepiColombo to initially monitor the proper deployment of the solar panel and the high gain antenna, but they can be also used for outreach. And I will hand over to Jack to guide you through some of the images we took with our monitoring cameras.
Hello, everyone. Thank you. So yes, I'm Jack Wright. I'm an ESA research fellow, and I study the geology of the planet Mercury. And so I'm very interested in looking at images of it. And I also lead the sort of little subgroup within the wider team that tries to generate a little bit of public interest in the mission during its long cruise to Mercury. And one way you can do this is by using the monitoring camera images. So I'm going to show you 4 images and talk you a little bit through them. So we can zoom in and have a look here. So this image was taken 1 minute after closest approach. So the altitude of the spacecraft at this point was something like 177 kilometers. And at this time, the spacecraft is traveling 5 kilometers per second. So we wanted to image as soon after closest approach as possible to get that image as close as possible to the planet. But we also were passing over the division between night and day on the planet. This is the dawn terminator. So on the right-hand side of this image, it's in complete shadow. This is nighttime. And on the left, the planet is illuminated. And so this is sunrise on Mercury that we had to time. The timing of this image being taken had to be very precise in order to be able to capture this. And so there was some doubt among some team members when maybe we were planning this image that there would be anything visible. If we were too early, it would be completely in the dark and it would have been, a waste of our time. So when we saw this image, I think perhaps Johannes was most delighted of all to see that we had captured this image perfectly. So we can move on to the next image. So in this one, we can see this one's taken about 2 minutes later. And we can see in the center of this image, the Vivaldi peak ring basin on Mercury. And so Mercury is covered in impact craters of all different shapes and sizes. This one here, Vivaldi, is about equivalent in diameter to the distance between Cologne and Amsterdam. So I tried to come up with some German-centric comparisons for you here. I did the best I could. And what's striking about this feature is that it has not just a simple bowl shape like a crater that you can see elsewhere in these images, but it has this peak ring as well. And the formation of these peak rings is something that is still debated to this day at conferences like the Europlanet Science Congress, where we are today. So I can give you one example of how these things might form in case it interests you. When a normal crater forms, the explosion excavates a sort of bowl shape. But as the energy of the impactor increases, when you get to bigger and bigger impacts, the size of this bowl becomes so big that the strength of the material is unable to withstand against the force of gravity, and it collapses, and the material rushes into the center of the crater. And it can pile up into a central peak, but if that becomes oversteepened and unstable under gravity, then it can spread out like ripples on a pond, and then it is frozen in time eventually to make the peak ring that we see here. During the impact, so much energy is released that the rock almost behaves like a fluid. The particles are suspended in acoustic energy, essentially, but eventually it's frozen in time. And that's how a peak ring like Vivaldi can form. Now, you might be wondering, why is this object called Vivaldi? And so in case anyone doesn't know, impact craters on Mercury are named after practitioners of the arts. Singers, composers, dancers, you name it. painters, etc. And so that's why Vivaldi is an appropriate name for an impact basin on Mercury. And when we were planning the monitoring camera images to be taken during this flyby, we realized that we would take an image of another peak ring basin on Mercury, but one that had not yet received a name. And so we discussed among the team, and we decided that we would try to have this named. And you're looking at, in this image, the peak ring basin that you can see in the middle of the image that's just touching the high gain antenna of MPO. This was the impact basin that wasn't named, and so it was given the name Stoddart after painter Margaret Stoddart from New Zealand. And she was known for her paintings of flowers in her earlier career, but also her landscapes later in her career. And here's Maori Huts on the Lakefront by Mary Stoddart. And so that's where that name comes from. What's interesting is that the arts is one of the sort of fields of human endeavor where one might have expected men and women to be contributing equally throughout human history. But disappointingly, my PhD student at the Open University in the UK, Annie Lennox, discovered that less than 12% of the names on Mercury are names of women. And so she has gone on a crusade to try and redress this problem. And so we were particularly anxious on the team that a name of a woman would be selected. And so we were very happy. For our previous flyby, we had a crater named after Edna Manley, who was a Jamaican sculptor. So we continue this work with MSB4. And the final image I want to show you is one of the entire planet. And the German connection I want to make here is that the South Pole area of Mercury, which is at the top of this image here, is named after J.S. Bach. There's a Bach crater in near the South Pole of Mercury, but everything south of 65 degrees south, that whole South Polar area, is named after that crater as well. So this is the Bach quadrangle of Mercury we're looking at here. And the geological point I want to make is that BepiColombo here has captured an image of the whole planet from the dawn terminator that we were looking at zoomed in earlier, but all the way to sort of Mercury midday, which you see at the left. And you can see that the character of the planet's surface appears to change from right to left across this image. And this is entirely to do with the illumination conditions. Close to the terminator, the shadows are long, and this emphasizes subtle topographic features. And you might be able to see that the planet is covered in these sort of wrinkly, long, waving topographic features. And these are the surface expressions of faults on the surface of the planet that form as the planet cools, its surface buckles up and generates these sorts of wrinkly features. They're emphasized whenever the shadows are long. On the left, you'll notice that there are impact craters that have these bright material radiating away from them. This is a brightness contrast of fresh material that's been deposited after young impacts were formed. And these sorts of contrasts in the surface brightness are emphasized whenever the sun is directly overhead and the shadows are short. And as a geologist, we need to have images of both kinds in order to be able to understand the surface completely. And so I look forward to looking at scientific data from the symbiosis instrument on BepiColombo, and it will have to image the planet under these two different conditions. But MCAM was able to do it at low resolution, but all in one go.
Okay, thank you very much, Jack. And now we are going to Isabel, and be prepared that you now hold your glasses, because I told you that our stereo camera is blocked, but nevertheless, the group Isabella is working with is able to do fantastic things with our data. And now I would like to hand the floor to Isabella.
I'm Isabel Krüll. I'm here with the image analysis group from the TU Dortmund University, and I'm currently doing my master's in Bremen in space science. So our group at the TU Dortmund University has already done for the last flyby constructed a 3D surface map of a snapshot. So also this time we did it again. We used this snapshot from MCAM2, which was taken about 17 minutes after the closest flyby. And yeah, here are also visible the Raphael crater and the newly named Stoddard crater. And yeah, first step we did, we had to reproject the image, which was done by Jack White, and to align it with the coordinate system of Mercury. And because here we see a image of a sphere, but we need the correct angular projection for yeah, to apply our algorithm. So yeah, the result we can see on the left side, and also we shows a region in the middle of the image as yeah, our region of interest, because the upper part of the image are a bit too blurry, and in the lower part of the image there are too many shadows. So this is not so suitable to apply our algorithm. Yeah, so our algorithm is shape from shading. It uses the brightness information of the image to construct a 3D surface map. And yeah, you can kind of imagine it like a wrinkled piece of paper. The brighter part are tilted towards the light source, and the darker part are tilted away. And that way we can then construct a 3D surface map. So here you can again see the region of interest we chose. And then my colleague Kai Wolfrath applied the shape from shading algorithm to this scene. And the result we can see on the left, this colorful 3D surface map, where the bluish parts represent deeper parts up to a depth of 2,900 meters. And the reddish and yellow parts represent higher parts up to a height of 3,400 meters. We used this information, the so-called digital elevation model, to create a stereo anaglyph. So now is the time when you need the glasses. And yeah, you can see the 3D effect. It's a bit exaggerated, about 10 times, so it's yeah, better visible. I hope it works with the yeah, by the way, it's important that you use the red color on your left eye, otherwise it won't work. Yeah, I hope you were all able to see the 3D effect. And besides, we also created a video with the game engine Unity. This was done by my colleague Moritz Tenthoff, who's sitting in the back. Yeah, so he created a virtual flyby over the surface. And at the beginning, we will see the sun rising over Mercury's surface. And then the surface is rendered in real time. And it will show the two craters, Raphael and Stoddard, and also our high quality digital elevation model. And at the end, when the illumination geometry is the same as it was during the flyby image, the digital elevation model will look like the flyby image. Yeah, so enjoy the video.
Great. Thanks very much, Isabel. So yeah, you may have seen in the list of topics that we're covering today. We've got a mysterious work of art at the end. So just briefly before we move on to that, just the mission, of course, is a collaboration of the ESA centres in the Netherlands, Spain and Germany, our colleagues in Japan, partners in industry, and of course all the instrument teams on 3 continents. So the images that you've seen already taken by MCAM have been put together into a movie. And I hope you'll enjoy the next couple of minutes in this movie put together by Mark McCaughrean with a suitable background music, given the one of the craters that's obvious in the.
Yeah, these videos are recently published during the last half an hour via our ESA web pages. And so if you want them, go there and download them. Our next milestone is 1st of December, the next flyby. Thank you very much. And if you have questions, we are there for you.
Thank you so much, everybody. There's so much information, so much, all very exciting stuff. Great. Do we have any questions from anybody here in the room? I think you've stunned them. So all of that information, all the videos, all the images, they're now available online. There's
so not everything. So the movie you saw at the end and the 3D flyover as well, and then other products will we'll release them over the coming couple of weeks, I believe.
Great. We're aware that you've got to get back to sessions starting at 2:30. Yes, so you've got a little bit of time, but not very much. I think it seems that we are, I think, overwhelmed by all the information.